So first, I would like to congratulating you on getting the GSR award. So maybe you can tell me a little bit about yourself.
Sure. So my name is Arai, and I am from Kazakhstan. I was born and raised there. I went to an undergraduate called Nazarbayev University. It is named after our first president, and we were the first class actually. So right after graduation, I came here to Pittsburgh, and I've been studying in chemistry department for the past 3.5 years.
Okay. So which group you were in when you were at Pitt?
I am in Kenneth Jordan's group, and we do electronic structure theory calculations.
So can you tell me a little bit about your research?
Sure. So if you think about everything that is surrounding us, it is made out of molecules, right?
Yeah.
And molecules, when they accept an extra electron, they become anions. And whenever people think about anions, they usually think of the anions that we study in chemistry classes, which are valence in nature. They bind to valence anions that are, they bind to valence orbitals, and they are bound by short-range interactions. But in addition to those, we also have long-range interactions that are, for example, electrostatic or correlation interactions. And excess electron can be bound with those, via those interactions, into non-valence orbitals. So this is the subject that I'm studying. So I've been doing a few projects that are related to non-valence anions of various kinds. So if you think about a buckyball, C60 structure, it does not have a dipole moment. It is consisting of 60 carbon atoms. It is completely symmetrical, and there is no dipole moment. But this molecule will still have an anion that is non-valence in nature. It will be bound by correlation interactions. And this is what we're studying. But C60 is a very interesting system, but it's also very large and it's complicated. So we often make smaller models that we would apply various methods to study. So, for example, one of the models that we study is water-4 system. It is completely symmetrical. There is a D2H symmetry, which means it consists of two dimers, and these two dimers are getting closer or further from each other. And as it does, we study what happens to the energy. At long range, there is electrostatically bound anion. So the quadruple moment will be there. But as you push it closer, quadruple moment is not large enough to bind the electron. So when you account for correlation interactions, the molecule will bind the excess electron. Without a correlation interaction, it won't. And this is often not captured by many methods, either experimental or theoretical.
So I guess this is a dumb question, but how your research is related to quantum mechanics, or?
Well, I would say it's all about quantum mechanics. So everything in quantum mechanics, I guess, for me personally, it began with thinking of Schrödinger equation. And this is how I attempt to solve Schrödinger equation. So I described the correlation interactions, right? And Hartree-Fock is our simplest attempt to solve for the Schrödinger equation. And Hartree-Fock, by default, does not account for correlation interactions. It thinks of electrons as an average C. So if you think about, like, I'm an electron, and a lot of people are electrons, then you would only think about my interaction with the average C, but not with a specific electron in particular, which is the correlation interactions. That is why Hartree-Fock will not be able to capture these anions. So what we're studying is more advanced quantum mechanics methods that will be able to capture those. In particular, if you think about a lot of methods like multiplicity perturbation theory or couple cluster theory, they will try to improve on Hartree-Fock by accounting for correlation interactions. But because these methods will start from Hartree-Fock as the starting wave function, they will fail to bind these. And that is why we need other methods that would allow for additional orbital relaxation. One of the methods that we study is equation of motion coupled cluster. This method will perform a configuration interactions on the coupled cluster orbitals that are obtained from the neutral structure. And there are some advantages to this method is that it will only calculate the energy of the neutral molecule and then the correlation interactions on top of it. So it will not do two different energy calculations. One calculation, and it will give you the binding energy right away. So we study equation of motion methods a lot. They were developed by John Stanton.
Okay, that's very nice. Have you ever presented your research in our PQI events?
Yes, a lot. Actually, one of the first events that I ever presented my research was at PQI science event in 2016, so 3 years ago. Yes, and I really enjoy these events because I get to interact with people. It was one of the first experiences that I got, as I say, and I get to talk to people and get to interact with people from various fields. It's not only chemistry or physics, engineering. There are, for example, the science event, it includes people from all the departments in arts and science department. And
from UPMC.
And from UPMC too. So it's very interesting. You get to talk to people that are so experienced and then people that have no idea about chemistry. So you get to think about how you have to present your research so that it's understandable for people that have some background or do not have the background or have background that is probably better than mine. So that was interesting. And I also like not just the science events but the PQI events as well, because we get to go to these conferences that last for like 2-3 days, and we get to see people presenting from all over the world, essentially, mostly from the States, but there are also people coming from other countries, and it's really exciting because I can just come from my department, work there, and then just come here and listen for these interesting talks.
That's nice. And also I have 2 more questions. The first one is that, like, I know that you're very enthusiastic about your research, and then you also are doing pretty good. You get the GSR award, and you're doing pretty good in your research as well. Do you have any suggestions you would like to provide for like new grad students, like how to hold a high, a happy life simultaneously with enthusiastic research?
So I would say be like independent, learn to be independent. But the thing that was the most difficult for me when I came to grad school was learning to do research work that is outside of classes. So I'm so used to classes where you have instructors and you have books and everything that would tell you. Yes, exactly. You have answers. You know what to do. You know what you're expected. When you're doing research, you're doing everything completely independently. So you'd have to coordinate with your advisor, of course, and with people who are senior to you in your lab. People who were senior to me in my lab were helping me a lot in my first and second year. So I would say talk to people. If you have any questions, then ask people that are senior. Ask people from other labs what their experience is, and if you have anything that would bother you, talk to your advisor, because advisors are always there. They're not only there for the science stuff, they're also there for you.